embarrassment and related loss of business. Here's another public release that you may have heard of. So also in 2006, Netflix decided that they needed a good recommendation system. So to keep people on Netflix, they realized that you need to make sure people keep watching movies. And to make them watch movies, you have to make sure they get to the movies that they would like. So they built a recommendation system that, based on whatever you have rated in the past, will try to predict what other movies you might like, and maybe show those movies upfront to you. And they had a recommendation system in place. They realized it wasn't very good, so they decided to crowdsource this project, and they launched a competition called the Netflix Prize, where they would give away $1 million in an effort to improve their recommendation system. They also made available a fair bit of data. So I think they released something like 10 million ratings for about 20,000 movies for 500,000 subscribers, along with the dates when the ratings had been given out. And about a few weeks after they made available this data set to any researcher, two researchers at the University of Texas at Austin, Arvind Narayanan and Vitaly Shmatiko, they published a paper where they showed fairly conclusively that if, as an adversary, if I know a little bit about about some movies that you have seen and rated, I can actually find you in the database. So what Netflix released was, for each individual, their name was replaced by a pseudo identifier, and they released for every movie they watched the rating of the movie and the date it was rated. And what Narayanan and Shmatiko showed was that it's not that hard. I need to know very little about you to be able to identify you in this database. And how much is very little? It's actually really little. I need to know 2 to 3 movies that you saw, along with the approximate dates that you saw. So if you have a blog where you talk about the movies you have seen recently, I need to know 3 entries from that blog. That's enough. I don't need to know the date you watched them exactly. Within a week is fine. So if you have a blog where you talk about Blue Velvet and Dr. Strangelove, but you don't talk about some of the other movies that you have watched, well, if I have this database, I can easily find out what else you watched. This was, of course, a big embarrassment for Netflix. They had to face a lawsuit and pay $9 million in fines. And they were investigated by the FTC. They had to cancel the second Netflix prize that they had announced. So what I learned, the lesson I take from these 2 or 3 examples is that when you release some data, you don't release it in a vacuum. You release it in a world where there exists where a lot of auxiliary information is present. In some cases, such as AOL, that auxiliary information is actually in the data itself. In other cases, that auxiliary information can be obtained from other sources of data. And sometimes the auxiliary information may exist. I may know my friends. I may know what movies my friend has been watching. So even though it's not in some public database, a potential attacker may have access to this auxiliary information. And this was actually quite nicely summarized by the Presidential Council of Advisors on Science and Technology, where they were asked recently by President Obama to do a report on big data and privacy issues. And they wrote that it's increasingly easy to defeat anonymization by the very same techniques that are being developed for the many legitimate uses of big data. the same reason that big data is so powerful for analysis, the same reasons also make it very easy to beat all of these anonymization techniques. Okay, so in these examples, some microdata was released, individual level information was published. And you would think that if I don't publish anything, maybe I'm fine. You would be wrong. So Facebook, for example, collects a lot of information about you. They ask you about, for example, your sexual preferences. They give you an option to not share this information even with your friends. You have fine control. You can say, I want to share this piece of information with everyone, or with only my friends, or with no one at all. And Facebook can still use that information to target ads to you. And it does. So here's a paper that Alexandra Korolova, then a student at Stanford, wrote, where she showed that by targeting ads, you can actually learn information that people think is not public. So Facebook lets you target ads very, very well. So you can say, I only want to show ads to people who went to a certain college, work at a certain place, live in a certain zip code, are in a certain age range, of a certain gender, speak a certain set of languages. You can even say, I'm interested in a certain set of things. So it's not hard, if you work a little bit, to create a targeted ad which only targets me and no one else in the world. Even from what you learned about me today, it's probably not hard for you to come up with a set of attributes that uniquely identify me. Right? So you can create an ad which will only be shown to me. Now you add to that is interested in people of the same gender. This new targeted ad is either shown to nobody, because there's no such person, or to me, and only me, depending on whether I'm interested in people of the same gender or not. So by placing such an ad and waiting to see if the click happens, you can learn whether or not you can learn this private bit of information which I don't even want to share with my friends. In fact, you don't even have to wait for me to click on the ad. Facebook very conveniently gives you a report on your targeted ad. It tells you how many times the ad was shown. In one case, the ad will be shown 0 times. In the other case, the ad will be shown at least once. So it's not very hard to learn such private bits of information, even though no microdata was actually published ever by Facebook. So what this tells us is that even when all you do is act internally on the microdata, you are risking the privacy of individuals contributing to your database. In this case, the attack was somewhat active. You had to actually go and put an ad on Facebook. Maybe they could come up with some audit mechanisms. In fact, people have shown that there are passive attacks of similar nature that exist. So by just sitting and observing the people who like this also like on Amazon, and knowing a little bit of auxiliary information about some purchases I made, you can learn other purchases that I made. And this doesn't even leave a trace. So what this attack tells me is that even actions based on private information can be observed and revealing. So it's not just that publishing microdata is risky, even acting based on microdata can be risky. Let me give you one last example where nobody even acted on microdata. So we normally think that aggregates are not revealing. if I told you the population of the United States or the average salary of people in this in California, you would think that's clearly not saying anything about me. And that's true. If you reveal one of these aggregates, you are not revealing too much information. But when you reveal many of them, things get tricky. So here's a paper that appeared in 2008, August 29th. Don't worry about the title or what it says. It's clearly a technical, somewhat boring title. You would think this clearly has nothing to do with privacy. And yet, before this paper actually got published, there was the National Institute of Health released this fact sheet changing their data policies. They cite this paper in the first sentence, and there's a bunch of stuff, but the main upshot is that they decided, before this paper got published, to remove aggregate statistics files of individual GWAS studies from the public portion of the database. And it was not just NIH, similar as consortiums in Europe that were publishing such aggregate statistics also removed these data sets. So what was going on? So what's a GWAS study? It's basically, so a GWAS study is trying to find out how your genetic traits affect your, say, susceptibility to disease. The way you do a GWAS study is you take a large population of people who have a disease and see which genetic trait they have in more quantity than the general population at large. So when they publish data, they tell you of the people who were susceptible to the disease, in the first SNP, they were much more likely to have, here is the frequency of that SNP in the disease population, and here's the frequency of the SNP in the general population. So any one of these is a very, very large scale aggregate statistics. But there's a very large number of genetic markers, and these studies publish all of them. By putting them together, you can actually figure out whether or not any given individual participated in the study and was in the disease population. And it turns out, in fact, these single-dimensional, single genetic traits usually don't do a very good job of predicting disease. So people now want to do analysis of pairs of genetic traits and their predictive and how they predict disease. Guess what? It wasn't. Wang et al. Soon after showed that if you actually have this richer data, you can get an attack with way more statistical power. So what this attack shows is that even aggregate data can be revealed. There are privacy risks involved, even when all you release is aggregates. So notice that in all of these cases, the people doing the data release or people working with the data were experts. They weren't lay people, and these were people who were concerned about privacy. And yet, they failed in all these cases, and there are other cases which I haven't mentioned, and I'm sure there are other cases which are not even publicized because there's little incentive for anyone to publicize a privacy breach. And I think one reason they failed is that they were all using ad hoc approaches. They were saying, let's put ourselves in the shoes of the attacker, see what the attacker can do, try to do something to prevent that attack, repeat a few times until you are done. And these ad hoc approaches have the problem that they are limited by the imagination by your imagination. You don't even know necessarily what other sources of auxiliary information exist, what sources, what kind of attacks the attacker can come up with, and more generally, what sources of auxiliary information may appear in the future. So it's not surprising that these ad hoc approaches fail. And what I'll try to convince you today is that there is actually a better way to guarantee privacy and still release data. But before we get there, let me actually point to one more reason why all these approaches failed. It's what my colleague Cynthia Dwork calls the fundamental law of information recovery. So informally, the law says that if you allow the analyst or the attacker to get overly accurate answers to a large number of questions, then you just cannot avoid complete data leakage, no matter what you do. So in all of these cases, what the data publisher was trying to do was make available something from which an analyst can learn very accurate answers to a large number of questions. This law says that that inherently is the problem. There is a quantitative version of this law due to Denur and Nissim from 2003, which says, which kind of gives a quantitative form in a very simple setting, where say you have n people in a database, each of them has one private bit, and I answered n questions about this database. What they showed was that if you answer these questions with error, with additive error less than square root n, then as an attacker, efficiently I can reconstruct the whole database. I'll skip over the example. But the upshot is that what this fundamental law of information recovery tells you is that to be able to protect privacy, you have to keep track of how many questions you are answering and how accurate. If you give accuracy more than square root, if you add error less than square root n to n questions, you're already host. So either if you want very accurate answers, you have to answer a small number of them. If you want to answer a lot of queries, which you can do, the error has to be at least square root n.
Is that an asymptotic result as n gets very large?
It is, but in fact there are actually, the constants are very small. So I guess here I had an example. So if you have a database of 500 people and you answer n random subset sum queries, random counts, up to error of 5, then I'll be able to reconstruct a database where I have 400 of the 500 bits right. So even though the original formulation was asymptotic, it has been improved significantly since. In fact, there are even stronger versions available. So it could be that you answer 90% or 80% of the queries within error 5, and for the others you answer completely ridiculous. For the others you give completely ridiculous answers, and you don't even tell me which have more noise and which have less. Even then I can do these reconstructions. So there's a fundamental limit on giving overly accurate answers. I should say that square root n is not a very large number, and it should be, in many cases, acceptable to add error square root n. And as we will see, you can, in fact, answer a very large number of queries with error square root n and still guarantee privacy. Yeah?
I have a question. So were there actually semantic algorithms that were made to collect this data?
Sorry, could you repeat that?
Oh, so were there semantic pages that were used to collect this data? How was this successfully gathered and
So I guess this is a theoretical attack. This just says that if you publish something which will let an attacker learn accurate answers to a lot of questions. Then from those answers, I can actually reconstruct a lot about the data.
So are there any existing APIs, for example, or programming interfaces where you can actually call them theoretics on this?
Yes and no. I'll get to that towards the later half of the talk. There aren't any off-the-shelf software that are available. There is a bunch of research prototype systems that exist. Yeah. Okay. So just a reminder, ad hoc approaches to sanitize data are fraught with risk, and there is the fundamental law of information recovery.
Sorry, I have a question.
Yeah.
Is the previous result restricted to you having a query with, or a one-bit representation of a particular user, or does it generalize to any type of result? Because right now this is a massive simplification. I mean, normally you would have.
So I think the theoretical results that exist are usually restricted to the setting where the private bit in the database is a single bit. There are many variants of these which allow for richer data. And I think more generally, I look at this and I think of it as showing that giving overly accurate answers is dangerous. If there's a particular setting, maybe I could think about it and come up with an attack. Or maybe there are ways to sanitize it which are not susceptible to attack. But as we have seen from all these previous examples, ad hoc approaches don't work. So what I'll be talking about for the remaining however much time I have is a way to actually guarantee privacy protection and still not adding too much noise. Yeah.
Are there any theoretical results about estimating the statistical power you can get given the noise that you provide?
Yes, so there are several results of that kind. I don't think I'll have time to talk about them today, but I can give you pointers. So let me move on. I should actually just say before I move on, there are lots of settings where these large databases exist. So there's the government agencies, Census Bureau, Department of Education, Bureau of Labor Statistics. There are hospitals and insurance companies that have your medical records. And there are businesses that have a large amount of data about people. And all these databases exist so that we can analyze them, so we can learn about the Broad Street water pump. And yet, in all these cases, or in many of these cases, there are strong reasons to protect privacy. So these reasons could be ethical. You may just not want your customers to be on the front page of the New York Times. These could be legal reasons. In many cases, the government agencies are required by law to protect privacy. There's HIPAA and so on. There could be good business reasons. You may be able to, if your consumers care about privacy, it's important for you to make sure that your consumers don't show up on the front page of the New York Times. And finally, there are also data fidelity reasons for guaranteeing privacy. So as Kinsey showed several decades ago, the kind of answers that you get from people, if you give them some notion, if they believe that their data will be kept private, can be very different from the answers you get in non-anonymous service. So if you want accurate data, and you don't care about anything else, you should still care about privacy. Okay, so here's the setting we'll be looking at. So I'll be thinking of the database as a vector in D to the n. So there are n people in the database. Each person contributes one row to the database. So D can be anything, whatever structured or unstructured form. And instead of the analyst, having direct access to this database, the analyst will go through a curator. Think of the curator as an API to the database, and the analyst will ask a particular question to the curator. Tell me how many people smoke in the state of California. Tell me how many Mac users were shown this hotel when they searched for a hotel on hotels.com. And the curator will go to the database, compute the answer, and give back something that looks like the answer. In most cases, the curator will actually add noise to the answer. And so this is what we call the interactive setting. I'll be talking mostly about this interactive setting. We can also take things in the non-interactive setting when you want to publish something, but it's most convenient to think of the definition in this form. Okay. So what do I mean by privacy? I'll imagine two universes. There's the blue universe, where I am in the database and I have contributed a particular row. And there's the red universe, where I decide to take myself out of the database. So I've erased my data from the database. So there are two possible universes, the blue one where I am in it, and the red one where I am not in it. I will say that the curator is private if the analyst, when interacting with the database, can't tell which universe it is in. So analyst knows that he's talking to one of these two universes, but he is unable to tell which one it is based on the interaction. So this kind of definition is inspired by work in theoretical cryptography, and therefore it has this kind of simulation flavor to it. But I guess basically the point is, in the red universe, I'm not even in the database. So whatever the analyst does interacting with the red universe, it cannot learn anything about me from the database. What this privacy definition is saying is that the blue universe where I am actually in the database doesn't look any different. And because we kind of believe that in the red universe where I'm not in the database, the analyst doesn't learn anything about me, implies that in the blue universe also, if the curator is private, the analyst didn't learn anything about me. Okay, so so you can't give any utility if you want these to be exactly identical. What we will require is that they are nearly identical. So one leap that we will make is, and that we need to make, is that this curator will actually not be a function, but a randomized function. What do I mean by that? So the curator will toss some coins and use that randomness to potentially figure out how to add nuts. So there's some distribution that the curator is giving answers from, and the analyst sees one sample from the distribution. Right? So the analyst just sees the results. And we'll say this curator is private if the distribution of outcomes in the red universe and the distribution of outcomes in the blue universe are very close to each other. So this is what's called differential privacy. How close? So formally, I'll say this curator is differentially private if the probability of any outcome in the red universe and the probability of that same outcome in the blue universe are within a factor of 2 of each other. So imagine S as being the set of outcomes based on which the insurance company decides to increase your car insurance rates. If in the red universe, the insurance company didn't even learn anything about you. So the chances of it increasing your car insurance rates are pretty low. And this definition is saying is that it doesn't change significantly when you actually have a differentially private access to the real data. Yeah.
So what does this actually look like when you're the investigator has something like all the back users in the room right now? Like, what is that? Like, how is that?
So I'll come to that in 2 slides.
So this is like a likelihood ratio construct of some sort. But why won't happen 2? Just because it works well, or just because this is an example?
Good. So it doesn't need to be 2. What we really do is define. So the definition doesn't have a fixed constant. It has a parameter in it. This parameter C roughly quantifies how much information is being leaked about any individual. And we say that this interaction satisfies C differential privacy if this ratio is between 1 over e to the C and e to the C. Right? So think of C as very small, say 0.1. Then e to the C is something like 1 plus C. So if C is 0.1, this is saying the likelihood of any bad thing happening to you goes up by at most 10%. If it was 1 in 100, it goes up to maybe 1 in 99. So this is the complete definition of differential privacy. You imagine the red universe and the blue universe, a database X in the blue universe containing me, a database Y not containing my data. In the red universe, the curator satisfies C differential privacy if the distributions of outcomes are multiplicatively within an e to the C factor of each other. Okay, so turns out this definition has a lot of nice properties. First, you will notice that I didn't talk about auxiliary information. Why did I not? Because I didn't need to. This definition has the property that if you take the interaction, you take whatever you get from the curator, and then do whatever you want with it. You can run a join with some other database that you have available to you. You can post-process it in any way. The final thing still satisfies differential privacy. Even after doing all those things, you will not be able to tell the red universe from the blue universe. So this is a very strong definition of privacy, which is completely resistant to auxiliary information that you may have. There is another property of this definition, what we call composability. Roughly what composability says is that when I said think of C as the amount of information that is leaked, this says that that's the right way to think about it. So if I leak C amount of information in one interaction, and then again leak C amount of information in another interaction, this definition says that you've actually leaked only 2C amount of information. So what this definition lets you do is take these differentially private, we call them mechanisms, as units in a larger computation, and then you can reason about the total information leakage taken over the whole thing. So there is a Bayesian interpretation of this definition. What this the strong multiplicative guarantee implies that if, as a Bayesian, you update your posterior after interaction with the database, it doesn't change too much. And note that as you do more and more interactions with this database, this information leakage C accumulates. And that is what prevents you to run into the fundamental law of information recovery. If you are going to answer too many questions too accurately, every time you answer a question very accurately, you incur some information leakage. These things add up, and eventually you leak a lot of information. So if you have a system that puts a bound on the total amount of information leakage, that will not let you answer too many questions too accurately. Okay, so now I'll try to say something about, so I've hopefully convinced you that this is a very good privacy definition. I'll try to convince you that you can actually do something with it, that you can actually find the broad straight pump while satisfying this definition. So if you think of the trade-off between utility and privacy, we know that you can get a lot of utility if you don't care about privacy. So if you get zero privacy, you can get a very large amount of utility. You can also get a lot of privacy and no utility. If you don't publish anything, just throw the data, just delete it. You have great privacy, but zero utility. What we'd like is something in between. And what I believe is the case, what a lot of work in differential privacy shows, is that the trade-off really looks like this. You can get a lot of utility and a fair bit of privacy at the same time, especially when your database is large. Okay, so let me give you an example. So let me try to answer the question about what a differentially private mechanism looks like. Okay. So suppose you ask a question, how many people in this database satisfy a certain property? How many smokers are there in the state of California? Right? So this is what we call a count query. You are just counting the number of people satisfying a certain property. So P of xi is either 0 or 1, depending on whether xi lives in California and smokes. And f of x is just the total number of people in the state of California that smoke. What the curator will do when faced with such a query is it will compute the true answer and then add noise to it. What does the noise look like? It turns out it's convenient to add what we call the Laplace noise. So this is a noise distribution that looks like this. So it's a symmetric distribution with exponentially falling tails on both sides. So there's a formal definition of it, but don't worry about it. Why is this private? So turns out this is not very hard to see. So this function f, this count, has the property that the count in the blue universe and the count in the red universe differ by at most 1. Because the blue and the red universe only differ in having me or not having me. And I can only contribute 1 to this count. So the function evaluated on the blue universe and the function evaluated on the red universe differ by at most 1. So in the blue universe, I'm sampling from this distribution. In the red universe, I may go up by 1 and sample from this distribution. The form of this distribution, more or less by definition, gives me the multiplicative property. Because this distribution has an exponential tail, if I had a few minutes, I would actually give you a full proof, but it's actually, I think all of you can do this proof. It's not hard to show that the probability of any outcome, the probability that the outcome is this value here, between the red distribution and in the blue distribution are within an e to the c of each other. If I use c as a parameter of the Laplace distribution. So what have I done? I have computed the true answer and added some noise to it. How much noise did I add? Turns out the expected value of this noise is something like 1 over c. So if c is 0.1, I've added about 10 noise to this potentially large count. And note that if your database was actually a sample of a population that you were trying to actually learn about, just a sampling introduces a noise of something like square root of n. So this noise is pretty small compared to the noise that's already inherent in your sample. Okay, so this only answers one query. We normally want to answer more. If I answer k such queries, I can actually add k over c noise to each of them. Doing that will satisfy c over k differential privacy. But this is information leakage adds up. So over k of them, I satisfy c differential privacy. So you can answer a fair number of queries with noise increasing as the number of queries increases, this can be improved. So in fact, one simple example where this can be improved is what are called histogram queries. So suppose you want to know not just how many smokers are there in California, but in each of the 50 states. So these are 50 counting queries. But observe that I can only contribute to one of these counts. So the red universe and the blue universe can differ in any of these queries, but at most one of these queries. And taking that into account, you can show that in fact you can only, even though you're answering 50 queries, you only need to add 1 over C noise to each of them. So I guess I gave this example mainly to demonstrate that there is more than, that you can do more things than just adding Laplace noise. Unfortunately, I didn't have time to go deeper, but this is an extremely active area of research, and there's a lot more you can do. So if instead of answering, so if you wanted to answer k queries where k was actually even larger, you can always do that with noise which is something like square root of n, with some logarithmic dependence on the number of queries. So you can ask more queries than there are people in the database and still get reasonable answers to them. This is not limited to answering numerical queries. You want to analyze social networks and ask questions about social networks, questions about the graph structure of the network. You can do those things in many cases while satisfying differential privacy. We talked about Netflix in the beginning. You can actually build a recommendation system that satisfies the strong differential privacy notion and still does better than, for example, the baseline recommendation system in the Netflix price. You can do things like k-means clustering. You can do principal component analysis. You can run lasso. So this is a very, very active area of research. There's lots of papers being published on trying to do various data analysis tasks while giving the strong privacy guarantee. And if there's certain task that isn't here and you want to do tell me, and I will either try to point you to something or try to get people to work on that. Here are some actual examples. So here's a list of frequent queries to the Bing search engine. So these are generated in a differentially private way. So these are queries that have frequencies larger than a certain threshold. We did that mostly because uncommon queries are fairly boring. Here is a map of where people who work within 5 miles of San Francisco live, based on census data. Here is a differentially private version of this map. So this clearly has a bit more error than the original map, but you can imagine many settings where the analysis you want to do on that map can equally well be done on this map. I should mention some caveats. So firstly, we are adding noise, and there may be settings where that's unacceptable. Though you may want to ask in those settings, what about the sampling noise that's inherent? The noise may also be too large in some settings, and that may partly be inherent and partly be due to the fact that we don't have the best mechanisms that are possible yet, and maybe there will be. Maybe they exist already. Maybe we have found them. Maybe we haven't found them. One important caveat is that many of these problems do require fresh thinking. So you can't just take your out-of-the-box software or out-of-the-box algorithm and implement it and expect it to be easily made private. In many cases, you actually have to think about how to phrase your analysis so that it's so that it can be made private. There's no publicly available commercial out-of-the-box software, but there are several research systems that exist which implement many of these algorithms. Hopefully there will be more. And it's quite possible that whatever data analysis task you want to do is actually already doable with a small amount of noise. It may not be the case that by just adding Laplace noise, as I described, will give you great answers. And in many cases, there are more sophisticated techniques that already exist. And just because Laplace noise doesn't work doesn't mean that that differential privacy doesn't work. Let me then summarize what I have said. So I started with showing you some stories of why ad hoc sanitization is very risky, and yet privacy is very important. It has the good business, ethical, legal reasons to protect privacy. Differential privacy gives you a very strong definition of privacy, and you can already do a large number of analyses while satisfying this definition with very small amount of utility, especially for large data sets. I will just end with some pointers. So there's a bunch of courses at various schools on differential privacy that cover a bunch of these things. There's a nice survey in the Communications of ACM by my colleague Cynthia Dwok, who's so the first paper there was the paper that introduced this definition. And I guess there's a recent book out which should be available anytime. I'll stop it. Thank you.
Great, let's thank our speakers.
Two questions. One, can you publish at least the slide on these notes for the class?
Sure.
You're trying to do a non-interactive solution, so you're adding sort of randomized noise to various pieces of data in that database. So you're trying to publish it.
So that usually doesn't work too well. So if you were to try to publish something, I guess the question to ask is, what is the purpose of this publication? What are the kinds of queries that you would want an analyst to be able to answer? What the fundamental law of information recovery tells you is that if you want the analyst to answer any possible question accurately, then you might as well just publish data and learn. You're just fooling yourself by doing ad hoc sanitization techniques. But if you know what you want to do with the data, for example, in this case, so these are both examples of synthetic data. So this is data that you can publish. It looks like raw data, but satisfies differential privacy. It's good for a certain set of queries, not good for other sets of queries. Similarly, that data, as you can see, is good for geolocation queries, but from this you can't learn more information that may have been in the source.
More questions?
Does this technique of adding noise work on databases that evolve rapidly over time?
Yes, so that's a great question. So there are techniques for databases that evolve over time. You do pay an overhead, but it's only logarithmic in the time. So you can do things like a private version of Google Flu Trends. So you can plot the number of flu queries maybe cumulatively made over the past so much time. You don't pay too much overhead due to doing that. But it requires just adding Laplace noise at each step is not going to work. You have to do something more sophisticated.
Other questions?
Yeah.
If the database exists for the purpose of, let's say, presenting a bunch of aggregates about a raw set of data, instead of the Laplace noise that you're talking about, would even just presenting a weighted average for a particular day, instead of the actual count for that particular day, if you were to instead present a weighted average, would that be sufficient to meet the privacy standards that you're talking about?
So that's a very good question. So in general, no, but if you make some assumptions about the data, so if you are willing to believe that even knowing what the adversary knows, the adversary's prior is still, there's still enough randomness in the data, even after the knowledge of the adversary, then you can make statements like that. You have to make these additional assumptions, which I guess is somewhat annoying, and in some cases that may be justified. Personally, I feel like the price you pay for not making that assumption is not that large in many cases, and then you might as well just do regular differential privacy. But there is a variant of differential privacy which deals with exactly that kind of setting, where you take advantage of the inherent randomness in the data itself.
One last question, perhaps? Well, let's thank Kunal one more time. On behalf of the School of Management and the College of Arts and Sciences, thanks for participating in this seminar this year. The Brothers of the Jesuit Order have purchased snacks outside, and so feel free to help yourself on the way out and maybe talk further offline with Kunal. Thanks.